Okay. Hey, so this is just going to be a quick video elaborating on some of the differences between vapor pressure when we're looking at those non-volatile solvents or solutes that we talked about most in depth, and then going into a little bit more on our situations where we have two volatile solutes. And so, as a reminder, on Monday, we talked about this equation for the vapor pressure of a solution where, in this case, you just have a non-volatile solute like sugar, and you just find those mole fractions, multiply the vapor pressure of the solvent, you get the vapor pressure of the solution. And this is pretty similar to what you saw on your quiz the other day. We went through and did a question on this, and then I talked about cases where we have two volatile solutes, or sorry, a volatile solute and a volatile solvent. So we're talking about this right here. And we said that for these types of solutions, that the vapor pressure that you observe is the sum of individual vapor pressures. So it's the vapor pressure of, you know, substance A plus the vapor pressure of substance B. And we said that this is when you have something called an ideal solution. And what that means is that we have a relatively similar intermolecular force between all of our different combinations of A and B. So IMF, same between all combos of A and B, meaning that A with A, B with B, and A with B, they all are of similar strength. And we showed, this graph that talks about, the vapor pressure for one of these ideal solutions where you just take, mole fraction of A, mole fraction of B, multiply them by the vapor pressure of the pure, we can say solvent or just the pure substance, and it's just the sum. And we said, in a hypothetical where you have 3/4 of B and its vapor pressure is 100 torr, and you have a quarter of A and it's 10 torr, the total pressure is just 1/4 times 10 plus 3/4 times 100, and that was our ideal solution. But sometimes you can have solutions that behave in a non-ideal manner, and they do not follow that Raoult's law where P total is just simply equal to PA plus PB. In those cases, we're going to have a difference in the relative intermolecular forces that exist. So the first case is one where the solute-solvent interaction, so another way to say this, the interaction of A with B is stronger than the interactions of A with A and B with B. So I can say A interacting with B is stronger than A, and A interacting with B is stronger than B. Or, if you want to say this, you could say like this. Sorry, is equal to B. So the important thing here is that the interaction of the two together is stronger than any of the individual interactions. And in these cases, what we observe is that this total vapor pressure of solution is going to be less than what we predict by Raoult's law. And this is simply because what we're observing is that the delta H of mixing, if the interaction of A with B is strong, the absolute value of that is going to be greater than the delta H of A or the delta H of B. This is just another way to represent that you have a better interaction of A with B, and that you have, a lower energy state due to this enthalpy difference for this mixing case. And so in these cases where, delta H mix is greater than delta HA, delta HB, what you have is delta H of solution is lower energy. And if you have a lower energy state, what's going to happen is that your system is going to be less likely to move away than this lower energy state than when pure solutions or pure substances. And so because you have a lower energy state, if we think of, in all of these cases where you generate a vapor pressure, we're looking at, relative energy differences and really just about spontaneity. So that delta G of the delta H between two different conditions minus the T delta S between two different conditions. And let's imagine the process we're looking at is the conversion from liquid to gas. And so we know in the process where we're converting from a liquid to a gas, where gas is our final state, we have a higher change in entropy. So this is going to be a positive number because we're moving from the liquid phase which has some entropy to the gas phase, which has a lot of entropy. And we're competing against this delta H, which is really just the intermolecular forces between molecules. So we can just call them the IMFs. And so if we have a state that has a more negative delta H, what we'll see, just like we had with vapor pressure lowering, is that it takes a little bit more energy to get the same amount of vapor pressure. And because of that, we have a lower vapor pressure. And if you want to think about this more physically, if the molecules are having a strong interaction with each other in the liquid phase, they're not going to move to the gas phase because they have to give up that strong interaction. And so we can say this IMF is larger for mixes. And then we can just make that statement, stay in solution to maximize stabilized mixing. And then our other non-ideal solution, which we'll call condition number 2, is that where your solute-solvent, your A-B interactions are weaker than the solute-solute or solvent-solvent interaction. And what we see is the total vapor pressure in these cases is going to be greater than predicted by Raoult's law. And so simply, when you have this mixed state, it's going to be a higher energy state. And because you have high energy state, things are going to be favoring moving to the gas phase. So we're going to say favor movement to gas phase. And we can look at this symbolically and just say, delta H mix, absolute value of this is going to be less than delta HA or delta HB, just saying that it's this higher energy state. So there's an increase in enthalpy because of this mixing process. And what we can, say when we look at this transition, this delta G equals delta H minus T delta S for liquid to gas. If this is smaller than HA and HB, that means that delta H solution is going to be offering less enthalpic benefit just because it's going to be a either small negative number or more likely a positive number. So it's offering the small enthalpic benefit to stay in solution phase, in the liquid phase. And because of that, if you have what we might just call poor interactions between A and B, things are going to move to the gas phase to avoid these interactions. And we can just say that this delta H term for any individual A or B molecule in solution, this is going to be a smaller number or even positive. And so it's going to be easier to transition. And so this is all just boils down to if you have strong interactions between your two mixed things, they're not going to want to go into the gas phase because they're going to want to enjoy those strong interactions, because we're always about obtaining the lowest energy state based off of this delta G equation. And then if you have weak interactions between A and B, those molecules it's going to be very easy for them to get out of the liquid phase because there's no reason to stay in the liquid phase if they're not getting any energetic benefit from staying there. And so you want to maximize, a low energy state. And in the case of strong interactions, that means staying in the liquid phase. In the case of weak interactions, that means going into the gas phase. And so this is just what these curves look like. So if you have strong solute-solvent interactions, we'd see that we have a negative deviation from the dotted line is just the ideal situation. And it's the same for, each of these lines represents how much the pressure comes from each thing based off of its mole fraction. So everything's down below its ideal amount. So each is contributing a little bit less to the total mix, or sorry, to the total vapor pressure, which is the purple line. And then when you have the flip side of weak solute-solvent interactions, we see that everything has a positive deviation. So we can say this is a positive deviation, whereas this one was a negative deviation. And everything tends to have a higher vapor pressure just because it's trying to get out of solution to go into the gas phase where it gets to enjoy that entropic benefit, and it's not giving up much enthalpic benefit because of that. And so this is a question that just asks us to calculate the vapor pressure given that we have 3.95 grams of carbon disulfide and 2.43 grams of acetone. And we're just asked to calculate what is the total vapor pressure of solution. And so what we're going to end up doing here is we're just going to say our total vapor pressure is just going to be the vapor pressure from carbon disulfide plus the vapor pressure from acetone. That's what we're trying to find. And, each of these different components is just going to come from the mole fraction of each of those things times their vapor pressure of that pure thing. So we have mole fraction of carbon disulfide times its vapor pressure plus the mole fraction of acetone times its vapor pressure when it's pure. And so all we have to do here, we know that our mole fraction is simply just going to be moles of whatever we're interested in, let's say that's A, plus moles of A, divided by moles of A plus moles of B. And so if we want to find moles CS2, we're just going to take that mass we're given, 3.95 grams, divide that by the molecular weight, which if we look that up, we'd see that that's 76.15 grams. And we'd see that we have, in this case, 0.05187 moles of CS2. And then we can do the same thing for our moles of acetone. So we'd say that we're given in our problem statement 2.43 grams of acetone. Divide that by its molecular weight of 58.08 grams per mole. And you'd get that this will give you 0.04184 mole acetone. And just to make sure units work out, I'm going to put the grams per mole for each of these things here. And so if we're going to look at our mole fractions, we can say our mole fraction of carbon disulfide is just that number of moles of carbon disulfide, 0.05187, divided by 0.05187, plus the number of moles of acetone, which is 0.04184. We calculate that through, we get that's 0.5535. And then the mole fraction of acetone, you can just take, the moles of acetone, so 0.04184, divided by that sum, which is 0.09371, and you'd get that this is 0.4465. And then one thing to know is that if you only have two components, the mole fractions of those two components together is going to add up to 100% because they compose the whole solution. So you also can just take 1 minus the mole fraction of carbon disulfide here. And so finally, to solve this problem, what we're going to do is we're going to say P total is just equal to these mole fractions. So 0.5535 times the the vapor pressure for that, so 515 torr, plus the mole fraction of acetone, 0.4465, times the vapor pressure of acetone, 332. And we'd get that, this together is 285 torr. This together is 148 torr. And so our total pressure is simply going to be 433 torr. And then this is the ideal vapor pressure, or the ideal total pressure for this solution. And what we can see is if we go to this next slide, we said, here's our ideal and here's our actual vapor pressure. And what we are asked is this solution ideal? And then if not, what can we say about the relative strengths of the carbon disulfide acetone interaction versus the interaction of each of these two things with themselves? And what we're observing is that the ideal solution has a lower vapor pressure. So ideal is lower than observed. And so, right off the bat, we can say that this is not ideal since we don't have a matchup of our ideal and our observed vapor pressures. And if we say that our ideal vapor pressure is lower than what's observed, we're going to look for the curve where we have the purple line exceeding the expectation. So where the dotted line is less than the purple line, and that's the one where we have these weak solute-solvent interactions. So what we can say is that the CS2 acetone interaction is weaker than that of the pure substances. And so, this was just a little bit of diving into the cases where you move away from the ideal situation and you have your two possible options where you can have, let me bump this up a little bit more. Your two possible options where the relative strength of the mixed interactions are either, greater than that of your things alone or less than, and because of that, we observe different trends within the actual vapor pressures we observe. And so this is a type of question that you won't see as a normal question on an exam, but rather something that you might have as part of an extra credit question.